Okay, Assalamualaikum and good morning, everyone.
Morning, sir.
Okay, so before we move on to a new topic, so let's finish off the tutorial 5 from last week. So I left the final question. So let's continue and see how to answer the last question here. Okay, so the question asks you to find the transfer function Ts equals Cs over Rs by reducing the block diagram. Okay, so let's look at this block diagram. So here in this block diagram, first we need to find, as usual, we need to find the arrangement in cascade, parallel, and feedback. Okay, so from here, there are no cascade, parallel, and feedback arrangements. So we need to start thinking about shifting the pick-off point. Okay. So if we want to shift the pick-off point, so the only pick-off point that we can shift is this point here. So to shift this pick-off point, we can shift this to the right. Jump over several things like summing junction, the blocks, and also another summing junction. So we cannot shift the pick-off point. Okay, similar to this pick-off point here. If we want to shift to the left, so we cannot do that. So the only step left is to shift the summing junction. So we can shift this summing junction or this summing junction. So I prefer shifting this summing junction to the left. Okay, because we follow the general rules. But you can also shift this to the right. But then the calculation will be slightly different. Okay, so let's shift this to the left. So if we shift this to the left, then this line here will divide by s. Okay, so this line, the transfer function equals 1. So when we shift this to the left, then we divide 1 over s. Okay, we divide 1 by s. So let's write here. So shift summing junction to left. So we get 1 over s just to indicate. Then we can redraw the system. Okay, so after we shift the summing junction, then we can see the arrangement becomes slightly simple. It's slightly simpler than here. The arrangement at the back here, S and this S here is in cascade, okay? Because one of them is going forward and the other going backward. So this is in cascade, in feedback, sorry, in feedback. In feedback. Then this arrangement here, one over S, and the line, if you see clearly, it splits from this point, and then it meet again at the same summing junction. So this two, 1 over S, and the line here is in parallel. So let's simplify these two first. So we get parallel. So parallel 1 over S plus 1, okay? So this is minus here. So it's minus 1 over S plus 1. So this is only line, then the transformation equals 1. So we get 1 over S minus plus S over S. Then we get S minus 1 over S. And then for feedback, we have S, and then the feedback signal also S, the transfer function. So we get S over 1. So this is minus. So we get plus here. So S times S, so we get S squared. So let's redraw by inputting the new transfer function, the simplified transfer function. Okay, so we simplified the system into this. Then if you look, this block here and the next block is in cascade. So we can just multiply. And then when we multiply this, then let's multiply first. So this is cascade. Then we get S minus 1 over 1 plus S squared. Okay, just multiply. And then we can redraw just to see the new arrangement, okay, just in case we confuse. So RS Okay, so we get into this arrangement. Then here from here there is no again no cascade, no parallel, and no feedback, meaning that we need to shift. Okay, so we can shift peak off point. So if we shift peak off point, maybe we can shift this peak off point to the right. Okay, so if we shift this to the right, then the line here, which is the transfer function equals 1, will divide with this transfer function here. So we can write shift peak off point to the right. So we get 1 over this. So simply get s squared plus 1 over s minus 1. Then we can redraw. So after we shift this, then the line starts from here. Okay. Then from here we can see that the system has become a lot simpler. Tak adalah simple sangat. Okay, so these two here, s squared plus 1 over s minus 1 and s are in parallel. So this is negative here. So let's make this positive so that later on, bila dia gabung dengan ni, we want this to be negative. So negative times positive becomes negative. Okay. So parallel. So we have s squared plus 1 over s minus 1 minus s, sorry. Simplify. So we get 1 plus s over s minus 1. Okay, later on you can check, okay, whether I did it correctly or not. Then redraw again. Um, so this is minus, then this is 1 plus s over s minus 1. Then these two are in feedback, okay? So to get TS, we just feedback this. So feedback, then TS equals, so just feedback. Okay, so this is minus, then we have positive here. Simplify this. Okay, so this is the final answer. Later on, check balik betul tak. Okay, mungkin saya tersalah kira somewhere. Okay. Alright, so that's it about block diagram reduction. If you have any question regarding this, you can ask me later. Okay. So let's move on with our lecture. Okay, so okay, so we have learned about reduction of block diagram to simplify multiple subsystem into one single block diagram. Okay, so that's the method is important whenever you are given a system that has so many components or so many subsystems. So we want to get the final transfer function. Okay, so after we do all these things like deriving the transfer function from translational mechanical system, from rotational mechanical system, and then reduction of block diagram, actually we are going to analyze the system and to determine how the system responds to a certain input. Okay, so starting from this lecture, so from today's lecture, we are going into more into the analysis, the analysis of control system. So basically, before we can go further into the analysis, we need to look at the common system, common response, the system response. So there are two types of response. We have first order and also second order. And we have a higher order response, like third order, fourth order, and so on. But usually when we do control system, we tend to simplify the system to make it either into first order or second order. If you read more on control system from books, you will understand what I'm saying. Okay, but maybe because this is your first time encountering things related to control system or automatic control, so let's just take it by assuming that the system only has first order and second order system. Okay, so today we are going to look at the time response of first order system. So after completing this lecture, you will be able to understand the concept of poles and zeros. So the first one here is the most important. Okay, you must understand how to determine poles and zeros, and then determine the time response of first order system using only poles and zeros, and then lastly determine the performance parameter of a first order system. Okay, so what are poles and zeros? Okay, so we can use transfer function. So we have learned about transfer function, which is output over input. So we can use transfer function to obtain the time response. Okay, so to obtain time response, we need to use the partial fraction expansion, then inverse Laplace transform. We have learned this back in lecture 2A. So we can also obtain information regarding the time response from the poles and zeros. Okay, so what are these? So let's look at poles. What are poles? So there are two rules in determining the poles. Okay, so first rule is the poles are the value of Laplace transform variable s. So we have the variable s that we have seen since lecture 2a, but we don't know what is that s. Okay, that cause the transfer function to becomes infinity. So the poles are the value of s when the transfer function becomes infinity. Okay, so this is the first definition. And the second definition is the any roots of the denominator of the transfer function that are common to the roots of numerator. Okay, so let's look at an example. What are these? So supposedly you are given this transfer function gs equals s plus 3 divided by s plus 5 times s plus 2 times s plus 3. Okay, so we have this transfer function. So using the first rule, so to obtain the poles, so from first rule, it is the value of s when gs equals infinity. Okay, this is the first rule. So what are the value of s that cause this function becomes infinity? So the only values that cause this function to becomes infinity is when you have 0 at the denominator. Okay? Pembahagi dia kosong. So the values are s equals minus 5, minus 2, and minus 3. Okay, so when s equals minus 5, minus 2, or minus 3, then gs becomes infinity. So therefore, the poles of this transfer function are negative 5, negative 2, and negative 3. Okay, so that's the first rule. And then from the same transfer function, using the second rule, so although we can cancel s plus 3 because they are the same, so although we can cancel this out, but the value minus 3 is still the pole of the transfer function, even though we cancel this out. Okay, so this is just a reminder. So later if you cancel this out, you will see that s plus 3 is still the pole of the transfer function. So now you have to remember that to find the pole is to find the value of s when the denominator becomes 0. Okay, so that's the definition of poles. Now let's look at the definition of zeros. So using the first rule, it is the value of Laplace transform variable s, or the value of s, that cause the transfer function to become 0, or it's the roots of the numerator that are common to the roots of denominator. So let's look at an example. So using the same transfer function from previous example, so here using the first rule of zeros, it is the value of s when gs becomes 0. So the only way gs equals 0 is when the numerator is 0. So from here, the only way for the numerator to become 0 is when s equals minus 3. So when s equals minus 3, then gs equals 0. So the 0 of the transfer function is minus 3. Or we can use second rule, although we can cancel this out, s plus 3, because they are the same. But minus 3 is still the 0 of the transfer function. Okay, so now we have the two definitions. Okay, so to find poles, it's the value of s when gs equals infinity, and then zeros is the value of s when gs equals 0. Okay, so remember this until the end of this semester. Okay, sampai habis exam. Lepas tu nak lupa hantar situ. Okay, so let's look at an example, another example. So we have this transfer function s plus 7 divided by s plus 1 times s plus 1 times s plus 3. Okay, so the 0 is minus 7 and the poles are minus 1 -1, and -3. Okay, so here we have 2 minus 1. Okay, even though there are 2 minus 1, you have to still write 2 times -1, okay, 2 kali. So let's say if you have s plus 1, s plus 1, s plus 1, so many times. So you have to write all of them, okay? So the poles are -1, -1, -1, -1, and so on, okay? Even though they are repeated poles, but later on, after midterm break, we will see these repeated poles are important, okay? Although they are repeated. So you have to write all of them. Okay, so if you write only 1 minus 1, then jawapan salah. Okay, your answer is not correct. Then let's look at the second example. So you have the transformation s plus 13 times s plus 3 divided by s plus 11 times s plus 2 times s plus 9. So the 0, minus 13 and minus 3. And then the poles are minus 11, minus 2, and minus 9. Okay, simple, easy peasy. But in exam, your transformation is not given in factorized form. Okay, usually they will be given in complete form. Okay, in a polynomial form. For example, like this one. Okay. Okay, so you are given in this form. Okay, divided by something. So you need to factorize using calculator. Okay. So kita ada calculator, gunakan calculator, factorize it. Okay. And your zero and poles can be also in complex number. Okay. So complex number. So I think you have learned complex number maybe in ODE or calculus. So we have, for example, A plus BI. So we have in complex number form. Okay, so your zero and poles can also be in complex number. Okay, so please remember this because maybe in the next lecture, maybe this Wednesday, we will encounter poles or zeros in complex number. Okay, now we have looked at the definition of zeros and poles. So now we can look at the in more detail about the time response of a control system. So the time response of a control system is the time solution of a differential equation. So we have the ODE. So in this case, we have ODE. We do Laplace transform. We convert into frequency domain. We perform partial fraction expansion. Then we apply inverse Laplace transform to get the answer in time domain. So the time response is basically the final answer that I explained just now, the answer in time domain. So the time response consists of natural response and forced response. Okay, so natural response is caused by the system itself, and sometimes it's called transient response or homogeneous solution, while the forced response is caused by the input, okay, input to the control system. So it is also called particular solution or steady state response. So if you still remember ODE, bagi yang tak fail lah, yang fail ODE tu saya anggap tak ingat lah. Okay, so we have sometimes we have ODE like y double prime plus y prime plus y, for example, and then we equal 0. Okay, so we can use characteristic polynomial to solve this ODE. Sometimes we have ODE yang macam ni. Siapa yang minat ODE, dia faham, okay, insyaAllah. So we have in this form, we have equal sum function in time. So when we have this sum function in time, your answer will consist of characteristic equation plus the particular solution depending on the input here. Okay, so bolehlah revise balik ODE, tak payah revise cara kira pun, just revise the two different types of ODE. Okay, we have homogeneous solution and also particular solution. Okay, so for a time response, usually the plot will be having this kind of curve, okay, S-shaped curve. So usually the input will be in the black line here, okay, the input. Okay, so we want the system to respond and to reach the black line here. But in real life, our system will not behave as what we want, okay? It will not reach this black line, but it will reach some steady state value, okay? In this case, this blue line here. So this blue line represents the steady state value of your system. So in most of the system, there will be a difference between the actual response and the desired response. Okay, so we call this different as the steady state error. Okay, so the curve here, the blue curve here, there are two parts. Okay, we have the natural response or the transient response, which usually represented by the first part here, in the curve part. And then we have the steady state response, which is represented by the steady part of the response. Okay, so we have the natural part and the steady state part. Okay, so this is just a theory. Tak adalah tanya dalam exam kawasan biru yang awal ni nama dia apa, okay, tak ada. Okay, so this is the procedure to obtain the time response. So we have looked this, we have seen this back in lecture 2A or 2B. So let's say you are given a mass spring damper system, our mass spring system. First, we draw the free body diagram, and then write the equation of motion. Then we can plot or solve the equation of motion to get the time response. Sometimes the differential equation is difficult to be solved manually, so we have to use Laplace transform. So when we apply Laplace transform, then the equation becomes in frequency response. Then we apply the concept of transfer function, which is to separate, okay, the input and output to get the transfer function. Then we can apply partial fraction expansion and inverse Laplace transform to obtain the time response, okay, to obtain the same answer. So why we need this? Because as I said earlier, sometimes the differential equation is difficult to be solved manually. So we need to use other method, which is Laplace transform. So let's look at another example, okay? So let's say if we have this transfer function that relates CS with RS, but RS is given as 1 over S. So we want to find the time response. So basically we want to find CT. So we want to find CS first and then apply inverse Laplace transform to get CT. So firstly we find CS and then expand using partial fraction and then perform inverse Laplace transform and then we get CT. So let's look at the steps, okay? So first we find the transfer function CS over RS. And then we get CS by rearranging GS times RS. So what is RS? Okay, so RS is given here, but RS is input, okay? So the input can be anything, okay? But in this example, it is 1 over S. But there are many types of input. So we have step input. So the step input, we call it, we define it as RT equals A or a constant. But if we convert using Laplace transform, we get Rs equals A over S. And then we can have RAM input. Okay, so RAM input is A times T. So the second graph here is RAM input. If we apply Laplace transform, we get A over S squared. Or it can be in sine input. Okay. So basically the input can be anything, but you need to look at the question, what inputs are given. Okay. So in this case, you are given step input. Okay, from the first example here, you are given step input. Okay, but sometimes the question might give you ramp input and so on. Okay, so here our Rs is 1 over S. So when we have A equals 1, then we call the input as a unit step input. Okay, so if you are given unit step input, meaning that it's 1 over S. So we apply the apply this into the transfer function. So we get Cs equals 1 over S times S plus 2 over S plus 5. Then we apply partial fraction expansion. We find A and B. We get the fraction that has been separated. Apply inverse Laplace transform. So we get the time response Ct. And then from the time response, we can plot the graph. Okay, C versus time. Okay, the time response versus time. So here is an example of the time response. So we have the curved part as the transient response. The steady part is the steady response. Okay, so we have two parts. Okay. Okay, so this is just an example how to apply things that you have learned. Okay, so from the transfer function, from the example, if we look back at the time response and also the fraction here that you have separated, then we can see that we can use the poles and zeros to obtain the response of the system. So for example here, the first part here, over S. So the poles are, the pole is S equals 0. So you plot here in the S plane. So an S plane is a plane that has real value on the X axis and the imaginary value on the Y axis. Okay, sama macam imaginary Argand diagram. Okay, imaginary number. So here the pole is at 0. Okay, and the second part here, we have 3 over 5 divided by S plus 5. So the S plus 5 here is actually pole is at -5. So we can plot the pole at -5 here. So if you look at the system, the original transfer function here, so we have S plus 2. So the 0 is S equals -2. Then we can plot the system 0 at -2. So we represent pole using cross X or X. And we represent 0 by using circle symbol, okay, circle. So from here, we can see that the input pole, which is the input here, 1 over S, generates the force response, okay. So it will generate the force response, while the system pole, which is -5 here, will generate the natural response. So similar to what I said earlier, but in a different definition. Okay. So system pole generates the exponential part. Okay, so it generates this exponential part, while the input generate the constant part here. Okay, so this is just to explain to you the different parts of the time response. Okay, so both zero and pole generates the amplitude of time response. Okay, later on you can read more and try to understand. If I say, maybe you don't get it, but later on you can study by yourself. Okay, okay, so let's look at the order of control system. Okay, so we have looked at how to use pole and zero to determine the system response. Okay, so now let's look at the application, towards application by looking at the order. Okay, so in this case we look at first order, but before that, what is order? Okay, order of a control system. So the order of control system can be determined by the highest order of differential equations, or the highest differentiation. Okay, so let's say if you have double prime, y double prime plus y prime equals 0, so the order of this equation is second order. Okay, because you have the highest prime is twice double prime. Or the order of the system can be determined by the number of poles. Okay, so if you have two poles, then it is a second order system. If you have one pole, then the system is first order system. So we can look at the ODE, and also we can look at the transfer function. Okay, now let's look at first order system. So first order system meaning that the equation has one pole, or it has y prime only. Okay, y prime plus something equals 0. Okay, so let's look at a system that has this transfer function. Gs equals A over S plus A. So here we have only one pole, so meaning that the system is first order. So firstly, we can plot the pole on S plane. So first we find the pole, so pole is at minus A. Then we can plot this on S plane. So you just put cross on the S plane and put minus A. So this minus A here as a pole. So if you solve by inspection, so we have CS equals A over S plus A. So we get this by performing partial fraction expansion. So apply inverse Laplace transform. Then we can find the value of K1 and K2. Then we get the time response equals 1 minus E power of negative AT. Okay, so this is just a generic step. I think I don't have to explain more, but later on you can see it by yourself. Okay, so the time response is this. So for a first order system, if you have this transfer function, then the time response is this. Okay, so this is some sort of like formula. You don't have to perform partial fraction expansion, inverse Laplace transform, and so on. If you have this transfer function in this form, then the time response will be 1 minus E minus AT. Okay, then the response plot will be as in this figure here. Okay, so this is the general formula for first order system. Okay, so macam hafal lah. Okay. Okay, so from the time response, we can determine the performance of a first order system. There are several key performance index that describe the performance of the time response of first order. Okay, so firstly, we call the term the time constant. So the time constant is defined as the 63% of the final value, or somewhere here. Okay, somewhere here. and the value of time is equals 1 over A. So time constant, PC, always equals 1 over A. Okay. If you have this transfer function, A over S plus A, then the time constant is 1 over A. Okay, that's it. Hafal je. Macam mana dia derive? Tak tahu. Kena baca buku. And then the second performance parameter is the rise time. So the definition is the rise time is the time taken to rise from 0.1 to 0.9 of the final value. Okay, the example do some calculation. So the rise time is this formula. Okay, rise time 2.2 over E. And then lastly is the settling time. So the settling time is the value of time to reach 2% of the final value. So the settling time, the formula is 4 over A. Okay, so kalau keluar exam, tak keluar kot. Ni je lah formula dia untuk first order system. Okay, so let's look at an example how to apply the formula that we have learned for first order system. So let's say you have GS equals 50 over S plus 50 and input unit step input 1 over S. So from here, we know that the pole is minus 50. So by inspection, we know that the solution of the time response is Ct equals 1 minus E power of negative 50 times T. Then the time constant is 1 over A. The rise time is 2.2 over A or over 50. And the settling time is 4 over 50. Okay, simple. So this is the this is how you find the parameters for first order system. Okay, but you have to look at the transfer function. It must be in this form, A over S plus A. Okay. Okay, so that's it. So before we end the class, let's look at tutorial. Okay, tutorial related to first order system. So I discuss tutorial straight away because the question is quite straightforward for this tutorial. Okay, so if you look at the first question here, so determine the time response and performance parameters of the following system. So we have first question, GS 200 divided by S plus 5 with unit step input. Okay, so we have GS 200 over S plus 5 and RS equals 1 over S. So we know that the general transfer function is GSA over S plus A. But our transfer function is 200 over S plus 5. Okay, dia lain sikit. Okay. So let's convert this into A S plus A. So if you compare, then A equals 5. So let's make the numerator becomes 5. Okay. So we have 5 over S plus 5. So we have the remaining 40. Okay. So 40 times 5 becomes 200. So now we know that this is the the transfer function. Then we can find the time response of this part here without the 40. So the time response CT equals 1 minus E power of negative 5t. So we have the per kali here 40, so just multiply 40 here. So this is the time response. Now we need to find the time constant Tc. So Tc is just 1 over A. So if you look at Tc, Tc is 1 over A if you have this transfer function. But what happens if you have 40 times of the original transfer function? So if you have 40, it will only affect the steady state value, okay? But it doesn't affect the time constant or the time parameters. So the Tc will remain 1 over A. So it will be the same, 1 over 5. So same for the rise time. It will be 2.2 over 5. And then the settling time, 4 over A, will be 4 over 5. Okay? It will only affect the time response, but it won't affect the time constant, rise time, and settling time. Okay? Simple. Then later you can try question B, okay? So question A and B are similar, lebih kurang similar. So now let's look at question number 2. So determine the transfer function and performance parameter of the system with time response below. So here we have only the graph. So the question only gives you the graph, okay, without giving you any other information. So when you have graph, you have to remember the definition of the parameters lah, okay. So let's look at this, how to answer this. So first, we need to find the pole, okay. So we need to find the pole from the system, because from pole then you can determine the other response parameter, time response parameter, and also the time response itself. So firstly, we can use the concept of time constant. So time constant is 63% from final value. So look at the final value. So here is the final value. So maybe about 0.72. Okay, anggaran. So time constant, which is 0.63% or 63% of final value. So we get about I'm going to calculate it lah. Okay. So we get about 0.45. So from this value, cari dalam graph. Okay, so it's about here. So from the time value here, ni bukan time constant, okay? So this is just the final, the 0.63%. So the time constant will be this time here. So maybe about 0.15. Okay. Then from here, you can determine the other pole, okay? So time constant equals 1 over A. So the pole A equals 1 over 1.5, which is about 0.67. Oh, sorry, salah. 1 over 0.15.
Doktor.
Yes.
Untuk yang 63% itu dapat dari mana?
Dari soalan ni.
63. Oh, iya.
Dari definition of time constant, sorry. So the definition of time constant, it's 63% from the final value.
Oke,
Okay.
boleh. Oke.
Okay, so from here we get A around 6.67.
Persen tu dia fix ke memang dia
Definition dia fix 63% of final value.
okay.
Okay, then we get A, then we get the general formula. So the general formula is A over S plus A. But of course ada constant kat depan lah. Okay, so we have a constant here, and let's K. Why constant? Because if you don't have the constant, then the time response will be at equals 1, okay, the final value. But now the final value is at 0.72. So meaning that the scale down, okay, scale down. So the general formula, which is A over S plus A, meaning that the final value equals 1. Okay. So now we need to find K. Sebenarnya saya tengah tengok jawapan, saya pun tak tahu macam nak kira. Okay, so the final value is 0.72, and then benda ni, okay, yep. Okay, so this is the K. Okay, so this is your transfer function, but the original transfer function is as A over S plus A. Okay, so we have K here instead of A. So if you make this transfer function similar in this form, then you can factorizekan lah kan. Okay, so if you factorize A, so you get this part similar to the general form. So our final value is K over A. So the final value K over A. So we need to find K. What is K? So 0.75 times A. So we get 5. Sorry, we're going to calculator. So our A is 6.67 times 0.72. So it's about 4.8. So your general transfer function will be 4.8 over 10. So the time response CT will be 4.8 over 6.67. 1 minus E minus 6.67. Okay, so guna yang ni. Okay, so it becomes K over A times 1 minus E minus AT. Okay, guna yang ni. So we have this, then we can find the other parameters like time, rise time, 2.2 over A, and then the settling time, 4 over A. Okay, so this is just how to look from graph, okay? Tapi final tak keluar lah, so this is just a practice for you. Okay, so that's it. Itu saja untuk first order system.
Tapi yang ni practice untuk MATLAB kan, Doktor kan?
MATLAB, tapi MATLAB kita tak keluar first order system, kita keluar second order system. Tengok balik dalam soalan project. Okay, so thank you remind pasal MATLAB. So your MATLAB will be about second order system. So dah boleh start explore, okay? Explore, saya ada bagi link dalam project punya description. So try explore how to use MATLAB, okay? So of course I don't teach you MATLAB, okay? So like last semester punya student, and they complain that I don't teach MATLAB. So this is project, so I hope you can explore by yourself MATLAB, okay? So I teach you the theory, so you explore by yourself how to use MATLAB, okay? So it's a fair game lah. So I teach you theory, you explore lah dia punya the application part, okay? How to apply MATLAB and so on. So of course you don't know how to use MATLAB. So this is the time you have to explore, okay? So siapa yang tak cari MATLAB lagi, sila cari sebab your due date for project part 2 will be next week Wednesday, okay? Yang kali ni tak ada excuse. Hantar lambat, hilanglah 4 markah, okay? So even though it's a 4 marks question, but it's a free marks je, okay? For the second part here, because it's so simple, you don't have to do so many things, okay? You just use MATLAB and then do some manual calculation and compare between MATLAB and manual calculation. You don't have to cari reference ke yang macam part 1 hari tu terlalu malas nak cari reference, ada yang bagi link website, okay? So dah pesan banyak kali, still bagi link website, faham lah apa yang jadi nanti. So please find your MATLAB and please explore also how to use MATLAB. And if you want to start doing the assignment, doing the project for second order system before we learn from class, that's totally fine, okay? Because in class later you already understand what you are going to do, or you will understand what we are going to learn, okay?
Doktor,
So, yes.
saya keliru. Memang ada link kan, tapi buat dalam bentuk reference style lah kan.
Buat macam biasa je, ikut je arahan tu. Arahan tu kata kira manual kan. So you perform manual calculation and then guna MATLAB.
Bukan yang tadi doktor kata tadi part 1 tadi, bagi link. Tapi dalam link tu kita kena buat dalam format untuk reference kan, doktor, betul lah kan?
Saya tak nak link pun, saya sebenarnya nak journal je, journal tu. Ada orang tak bagi journal pun, macam tu lah maksud saya.
Tapi saya dalam report tu saya letak reference sekali dengan link dia lah dalam bentuk APA style tu, betul kan? Betul kan?
Tengoklah macam mana. Apa saya tengok dulu macam mana. Okay.
Journal tu kena masuk sekali dalam report ke doktor?
Saya minta kan dalam arahan soalan tu, please attach your reference journal and also your report. So
asing-asing kan?
Asing kan.
Okay,
nak sekali kan pun tak apa. Ada yang sekali kan, which is still acceptable.
Okay.
Ada yang bagi link Wikipedia, which is obviously tak acceptable lah. Ada yang bagi link buku. So buku is not acceptable. I want journal specifically asked in the question 2016 and above. Some of you might give 2016 and below. Tak nak lah, okay. So arahan clear. Kalau tak clear boleh tanya. Tak tanya maksudnya fahamlah arahan tu, okay. So for second part also, if you are not clear with the instruction, please do not hesitate to ask, okay. Just ask me. Tak tanya, saya anggap faham soalan tu, okay. So that's it for, sorry?
Dalam report tu saya letak reference juga, sekali dengan link dan juga saya attach sekali dengan journal.
Okay lah macam tu, okay je. Okay, so if you have any question regarding project or regarding the topic, please ask me, okay. So that's it for today's lecture about first order system. So on Wednesday, we are going to look at how to perform the analysis for second order system. Okay, so that's it for today. Thank you very much. Assalamualaikum and goodbye.
Salam doktor.
Thank you.
Thank you.
Thank you, Doctor. Thank you.
Yeah.